Okay, this is Thermodynamics. There's 4 people here. That's pretty small. There are 7 people, I think, registered. Hopefully, they're all going to be in the class, but we're sort of lucky we got to run this class at all. I'm glad we did. I was nervous for a little bit, but I don't know. Things are just so weird with COVID and stuff. I'm glad that they gave us a chance to just keep some stability here. I think that was the right move. 3 of the 4 people in here were in statics also, and the syllabus and everything is pretty similar to statics. I am going to go through that, so it's going to be pretty much the same old thing, but it'll only take half an hour or something. And then we'll get into a little bit of the start of thermo today. And before I start, just like in statics, I want to talk about Design Club for a sec. Okay, so this is starting this year, Design Club. We have a great fab lab at Normandale, an unusually great fab lab. And this is a way to organize, to take advantage of it, to make products over an amount of time. The idea is the students in this club will come, will bring ideas that you've had or build off of ideas that, I can help you with. We'll brainstorm together. I'll show you how to use the equipment you need for the products you're working on. We'll make a prototype. We'll come back, test it out together, brainstorm it together, go iterate on that until we have something we're happy with, which we'll then sell online, package, ship. The money that we make from it will just go back into the fab lab. But I think for people who are interested in learning about the entrepreneurial process, I think it's just going to be an amazing experience. You'll get to use equipment that it's hard to get a hold of. So yeah, think about it. I think it's going to be really good. And actually, just yesterday, I talked to a professor in Twin Cities Engineering who recently got a grant to work on products for sort of like lifestyle products to make just getting through every day easier for blind people. And he wants to work with the design club on this project. So there'll be money available if we need money for it, and it's going to be great. So anyways, think about it. A couple people have contacted me already.
What kind of equipment do you have? Is it milling or additive manufacturing, like 3D printing?
We have multiple 3D printers, multiple mills, including that Tormach 770 mill that can mill titanium steel. It's a really serious mill.
Are any of those printers resin?
No, they are, yeah. And a laser cutter, final cutter, there's also a printed circuit board mill, so that for working on electronics, so you start out, when you're working on electronics, you start out with a breadboard, plugging wires into it and whatever until you get things working. But then to actually like sell an electronic product, you don't want wires that people can pull out or can just fall out or whatever. So you mill it into a single board, a small little thing that has all the electronic components just built into this little board. It's a solid thing that then you can put in stuff that's going to be durable. We have one of those. And then just a lot of hand tools and stuff too. But it's a very complete fab lab, really nice. Any other questions about that right now? Even if you're not interested, just send me an email and let me try to convince you are interested. Okay, so that's Design Club. Oh, and as far as like scheduling and stuff, so tomorrow is the Normandale Involvement Fair. That's when people set up booths for clubs and stuff, and students come by, and you get students' emails, and start to contact people. So we're not gonna schedule meetings or anything until after that. But sometime, let's say within a week or something, after that's gone on, I'll be sending out group emails letting you know when meetings are going to be, or at least asking you to fill out like a form or something to try to figure out what the best meeting times would be for the most people and stuff. And we'll start getting it rolling within a week or so. That's the plan. Okay, so the first thing I want to do today is just talk about the structure of the class, go through the syllabus. I assume most people know how to get onto D2L, but the syllabus is on D2L. So go to the main Normandale page, go to D2L, log on. And the most important place to check, I would say check once a day, is when you get into the Thermodynamics D2L page. The first thing on the first page is the announcements. And every time I post something new, a lecture, or give you an assignment or something, it'll be up there. So you can just follow that. It's like, okay, there's something new here. If you don't see anything new on announcements, there's nothing new to worry about, okay? And then all of the individual documents are in the content section. Right now, if you wanted to read ahead or skim ahead or whatever, just see what kind of stuff we'll be talking about. There's a section here for old lecture notes. I think these are the 2018 notes. So you can go through one by one and just skim through what we're talking about. I don't think that's necessary, but I think it is a good habit if you're interested to read ahead a little. Gives you something to hang the new ideas on when we get to stuff. There's problems and problem solutions. I'll talk about those more later. There's some tables that we're going to use. And then course information is where the syllabus is. Okay, wait. Why does that say Physics 1104? This is not Physics 1104, but that's the right syllabus. So, okay, Thermodynamics, 3 credits. And a little bit of funkiness happened with the official classification of this class. It doesn't affect the credits you get or anything like that, so don't worry about that. I don't know if some of you noticed that in your registration, the class times changed and stuff. The way it's going to show up as far as credits is exactly the same. The way grades are going to show up is exactly the same. So none of that changes. But it's called a tutorial now just because of the low enrollment. And because it's called a tutorial, we're only officially allowed to schedule, like we can only meet for a third of the original time. Okay, well, I reserved this room for the rest of the time, and I'm planning to just come here as if it was the original class hours, give these lectures at the original, for the full original time. If you happen to not be able to make it for some of that, you might have noticed that I started this video before I started talking, we'll have videos recorded of my screen and my voice for every lecture I do. So you can always, if you miss a class, go back and watch that. But so the long and the short of it is I'm going to be here Tuesdays and Thursdays from 12 to 1:20 giving lectures, just like before it was changed to a tutorial format. The best way to get a hold of me is email. You know the room number. You're the people who made it to this room. The people who are missing right now are the ones who need to know the room number. Office hours. I have 3 scheduled office hours a week right now. Normally I would schedule 5 a week, but since things are still a little funny with COVID and everything, I'm going to set some time aside just to schedule meetings through Zoom. So you can meet come talk to me in the tutoring center during these 3 hours a week, or please feel free. I'm expecting this time to be filled, so please feel free to email me and we'll schedule a Zoom meeting or a meeting in my office or whatever. But I'm just only reserving the 3 so that we can be more flexible about it. So send me an email. I'll say say you want to meet. I'll say oh, does 3 o'clock this afternoon work? Yeah, then I'll send you a Zoom link or we'll meet at my office or something. Okay, it seems to work pretty well. The prerequisites are chemistry and physics 1. If you haven't taken either of those, come talk to me. You could probably get by fine without them, to be honest. The only thing that I would say you really need is Calc 1 for this class. The materials needed, there's no textbook for this class. Everything that you're going to need comes from the lectures and the notes that I'm going to give you. I just try to be really clear about what I think is important, what I want you to learn, well. I don't want you reading a million other pages of stuff that I don't care about that much. I'm just trying to boil it down to what I think is really important to remember. So the only material you need is a graphing calculator. Most people have Texas Instruments calculators, but there's a few other brands that are fine. If you've been thinking of getting a graphing calculator and you want recommendations, you don't need it for this class, but I would recommend getting one that does eigenvalues and eigenvectors. I think you would find in the next year or so that, starting in the next year or so, basically every class you're going to have in engineering is going to use eigenvalues and eigenvectors in some way. So it's nice to be able to do it right on your calculator. Although it gets sort of less important because now on phones and stuff, there are websites you can just go to and they'll do those calculations for you. But it's nice to have it on a calculator. If you don't have a calculator like that and you would prefer not to buy one right now, we actually have a bunch, 8 or something, brand new that we bought in the spring that we'd be happy to loan out to you. So come talk to me or email me if you would like to borrow a calculator. Recommended reference books. These aren't really for this semester. These are if you want recommendations for books for later on to go back and read. First, Moran and Shapiro, that's the textbook that I more or less follow as I go through this class. It's a good textbook. I like it. And then but it's expensive. It's a textbook. New it costs $200 whatever dollars. You maybe used, you can find it considerably cheaper than that, but it's still expensive. The one I think you should consider buying is the Shams Outline of Thermodynamics. I mentioned it in statics too. I mentioned it in every class I teach. Sean's outlines they do for every single class that you'll take in engineering and science. They cost something like $20. They have a million worked problems. They have not really full fleshed out descriptions of the topics, but kind of condensed summaries of the topics, which I find it's really what I like. I mean, I would rather read the sort of concise things in the Shams outlines than the really wordy things that are in most textbooks. So, and even for this class, just having all the problems with solutions in them can be nice if you want extra practice on problems, like while the class is going on. So I would recommend that. That's such a nice series. Okay, topics to be covered. So mostly this is just an introduction to the ideas of thermodynamics. So we'll talk about sort of energy conservation. We'll talk about entropy. We'll talk about power cycles, refrigeration, and heat pumps, which are sort of the three main practical uses for thermodynamics. And we'll talk about mixtures of gases briefly towards the end, and we'll talk about combustion and combustion engines sort of briefly towards the end too. The grading scale is most likely, I mean, it could be lower if scores are low overall, but it's probably going to be 92, 82, 70, 60. And like I said, in statics, the 92, 82 sounds high, but really more than anything, I think that's just what I've found works well because of the way I teach the class, the kind of questions I ask on exams. Like I said, I try to boil it down into a manageable amount of material. I expect you to learn that material well and thoroughly. And then the exam questions I give you are very reminiscent of the problems that you've been working on. And so people just tend to score well, like I don't give any exams where the class average is 56 or something, so that's all that means. I don't think you'll find that it's hard to hit these grade marks. The breakdown for the grade is 10% lecture quizzes, 10% daily assignments, 30% weekly assignments, 50% exams. And so now I just want to go through what each of these mean. So the lecture quizzes. So most of the exams, the weekly assignments, the daily assignments are problem solving things, math, like you're solving numerically for values. But I also, besides just the calculations, I want to make sure that you're taking notes, watching all the lectures, and going back, maybe even more important, and reviewing your notes from time to time. And so the lecture quizzes are the things where there's not going to be any problem solving, no number stuff. It's just going to be me asking questions about the lecture, just making sure that you're learning it at the level of detail that I expect. So it says most Thursdays, but maybe it's more like every couple weeks or something. But I'll end class with just we'll end class 10 or 15 minutes early. I'll hand out a quiz with 5 or 6 questions on it that are just sort of short answer questions. What's define the first law of thermodynamics, that kind of stuff that will come up in the lecture. One thing about it, so it says Thursdays, but now that we have this, officially we have this tutorial format, we don't really technically meet on Thursdays. We only meet Tuesdays for 50 minutes, you know. So if everybody's planning to be here fully Tuesdays and Thursdays, I'll just keep it like this. But if you've changed your schedule or whatever and you can't make it every Thursday or that kind of thing, please just talk to me or send me an email, and I'd be happy to, you know, move the lecture times to another time or let you take your quiz in the testing center or something like that. So just let me know. But for now, I'm planning to just do it at the end of the class on Thursdays. Oh, and so the lowest 2 quiz scores will be dropped. So if we have a total of 12 quizzes, 2 get dropped, and your 10 best scores are worth a total of 10% of your grade. So each one of those scores is worth 1% of your grade. That's sort of how it works. The daily assignments, this is really the heart of the class. This is where all of the learning, for the most part, takes place. So after every lecture, I'll tell you what problems I want you to work on. I'll give deadlines just to sort of encourage you to stay on top of things and not get behind, but really none of the deadlines are like hard deadlines. If you need a little extra time on something, you can let me know, but I mean, you can always take extra time. And you are going to turn these assignments in on D2L. So you're going to either scan them and turn in a PDF or take pictures of them and turn in photos. But these daily assignment problems, I have full solutions written out for all of them. So the idea is that you work on all of these problems without looking at the solutions, but those solutions are there if you get stuck. So you can sort of look at it for a hint, then put the solution away and try to work through the problem again. That's the effective way to use the solutions. You could, of course, just copy down the solutions and then turn that in, and you'd get a perfect score on your daily assignments, but you wouldn't learn anything and it would show up on the exam. So that's a bad way to do it, you know. Okay, and all of those problems are already up here. You can look at, you know, so here's a set of 16 problems related to the first law of thermodynamics. And if you go to the problem solution section, oh, these are not all of them. Okay, so I'll get that updated. I think somewhere I have full solutions. Otherwise, I'll just make full solutions. Right now, it looks like it's just sort of partial solutions for some of them, but I want to get solutions up for all of them. So I'll get going on that. Any questions about the daily assignments? So even though, so that's worth 10% of your grade, but don't think of it as worth, you know, it's worth a lot more than 10% of the grade because there's a huge correlation between how seriously you take these daily assignments and how you do on the exams. You know, that's really the, and how you do on the weekly assignments. That's what makes the daily assignments important. Yep. Not due today. Depending, I think probably I won't give you one after today. We'll see how far we get. But if we get far enough to do a couple of problems, I'll assign a couple of problems. But once the class gets going, I'll assign them after every lecture. Any other questions? Yeah.
Do they do the day of after lecture?
I think I usually give, like, make them do before the next lecture kind of thing. But like I said, I mean, I don't ever close them. I mean, you could turn them in 2 weeks later, and that's fine with me. It's just if you get in the habit of doing that, you're going to get behind, and then things aren't going very well, you know.
Yeah.
Any other questions? Okay, So now the two biggest parts of your grade are the weekly assignments and the exams. The weekly assignments are going to be problems. I'll give you a set of problems. They'll be cumulative, so I'm going to make you go back and answer questions related to old topics, because I think it's important to keep going back and reviewing material. I think that's how it sticks in your head. But I'll give you, say, 5 questions or something, 5 problems. The problems will be similar in difficulty and thought process to the daily assignments, but I won't give you solutions for these. And you'll have a week to work on them, and then you turn them in, and I grade them sort of like take-home tests, although since there'll be, say, 8 of them or something, and each one is only worth, say, 4 or 5% of your grade, something like that, not a huge chunk of your grade. But that's the idea of weekly assignments, just to make sure that you're learning enough about this material to do it without the solutions available. Question? Oh, okay, yeah. You'll turn those in the same way you turn in the daily assignments, either take photos or scan and turn in PDFs of the documents. In engineering classes, this isn't really an issue, but remember to show me all your steps. Like, don't turn in stuff that just has answers. I want to see your sort of reasoning steps. People call that showing your work. In a way, I like to think of it more as like, because what do I know? Like, maybe you can do a lot of that work in your head, but that's, even if you do it all in your head, I want you to give me a roadmap. You're trying to communicate to me how you're going about this process, and so in English, you write papers to show your thought process, and here you show mathematical steps to show your thought process, and that's what I want to see on these assignments. Okay, and then the last thing is the exams. There are 4 of those. The last one is during the final period. The exams are all cumulative, so even when we're in week 14 or something, the exam can have material that you did in week 1 or week 3 or whatever. So you need to be sure that you're refreshing your memory on that kind of stuff, and I will try to keep doing that with those weekly assignments. These are in-class exams. The dates of the exams are given here. If you get a bad score on one of your first 3 exams, and you get a higher score on your 4th exam, I'll replace your lower score with your 4th exam. So if you really mess one up, it doesn't have to totally derail your grade. Also, if you have an unexcused absence to one of these exams, that's the way to get a score for that exam that you miss. But let me know if you know that you can't make it to an exam, and we can make accommodations for that. Any questions about the exams? Okay. Okay, a word about cheating. There are really 2 ways that you can cheat. You can copy someone else's work, or increasingly the problem has been, that I've seen, has been using Chegg. I feel like it's pretty easy to tell when somebody has just copied something off of Chegg. There are ways to hide it, but in order to be good at hiding that you've copied something off of Chegg, you, for the most part, have to know the material well enough that you wouldn't have had to do it in the first place, So that website is, I kind of can't believe that it's legal. I know that there are ways to use resources like Chegg in a totally clean way, but it's just so like enticing. And I've had so many, I mean, I've had so many people in the last couple of years turn in stuff that's just obvious. And our department has an account on Chegg, so you just plug stuff in and you find it and you look and you're like, and actually like half the time, the people who give the Chegg solutions have made mistakes somewhere. So you're like, oh yeah, here's where they did this calculation that's wrong, and exactly like the students, it's pretty simple, you know. Yeah. So I would love to be in a world where I didn't have to mention cheating, but it comes up every once in a while. For the most part, it doesn't come up in engineering as much as it does when I teach physics 1, but hopefully we'll avoid all that. For canceled classes, like later in the semester, if we start getting snowstorms and stuff, the best thing to do is just look on D2L. I'll put something in the announcements if class is canceled, but you can always call this number and see if classes are canceled or something. And Normandale has an amazing OSD office for students who need so many different types of like resources for testing or studying or disabilities, extra time for tests. So if you think you might have a need for taking tests or something, just go talk to them and they can help you out. They're such great people. I love that office. They make the whole process so easy and streamlined. So that's at the bottom of the syllabus if you need that phone number or something. Okay, anybody have any questions? Yeah. December.
Yeah, I mentioned that too. I thought that's finals week.
December 15th. Okay, that does look suspicious. Well, I better go back and figure out what days we're really taking those. Thank you. Looks like I'll probably have to change that. We could just do exam 3 and exam 4 at the same sitting as a time saver. Okay, yeah, that's probably wrong. You're right. Any other questions? Okay. Well, let's just start talking a little bit about thermodynamics. Okay, so thermodynamics. Oh, and I didn't say this, but the way I think you should think of this the same way as if I was writing it on the whiteboard, but I'm going to do all the stuff on here. You know, so take notes just like I was writing it on the whiteboard, but these notes that I'm writing are going to be available to you in PDFs after the class, and this is all going to be on video, so that's why I'm doing it on this instead. So I want you to think for a second about a couple of things. What is thermodynamics? What would you guess we're going to study in this class? And second, in your major, in your discipline, what types of problems would you guess thermodynamics comes up in? You know, where does thermodynamics come up in your discipline? Okay, so let's just take a minute or two, think about that, and then I'll talk a little bit about just an overview of what this is. Anybody want more time to think about it? Okay, so what is thermodynamics? So really, practically speaking, I mean, it could mean virtually anything in physics and chemistry or whatever, but practically speaking, it has to do with cases where you're exchanging mechanical energy for thermal energy in some way.
Yeah, for dynamics would mean systems that aren't static, so it's got to be changing or in motion.
Yeah, and so if there's no exchange of thermal energy, you would tend to just call that dynamics, you know? So it would be cases where you're using the transfer of heat across a boundary or something to cause some kind of kinetic motion, yeah. Yep.
Does the running of energy through circuits technically count as regard?
If you are in the cases where you're thinking about the thermal energy, then yes. In the cases where all you care about is the current or that kind of stuff, then that would tend to just be electricity, So exchange of mechanical energy for thermal energy. And there are really three main types of cycles that are included in this.
Remember, there's the Otto cycle.
So that's a sub branch of what I'm going to talk about. I'm talking more generally, yeah. Yes, there are several very specific types of cycles, but they fit into these three broad categories. The first is the power cycle, which is like the Otto cycle.
The Otto and heat flow, and the other one.
Yep. So what's happening in a power cycle, let me give the names of them first, and then I'll talk about what they are. And then the second is the heat pump cycle. And the third is the refrigeration cycle. And these two, the heat pump and refrigeration, are really the same cycle. Yeah, or that's one way to think about it, or you can think about it. I think of it as like it's the same. It's just like where your important stuff is. There's a cool side and a hot side, and you either have the important stuff and it's like, is the cool side important because you have carrots in there, or is the hot side important because you have cold people in there?
Yeah.
Okay, so the basic way these things work is So how do these work? And it's based on this idea. If you have a piston, we're going to draw this piston a lot. So there's the cylinder. Here's the piston inside the cylinder. Okay. And then there's a gas sealed in here. I drew it as a cross section, but you can think of it as glass or something. That gas is sealed inside there, so no material can leave. And let's say that the walls are well insulated. So that gas can be kept at any temperature, okay? So the first thing is, what happens if you heat up the gas? What happens to the piston?
So first off, well insulated, this makes it thermal.
Okay, so let's say this part is well insulated on the walls, but you can still add heat to the gas. So that is confusing. You're right. Forget about that. So yes, if you add heat to that gas by like putting a fire underneath the bottom of it or something, the gas expands. And the piston rises. Okay. All power cycles are based on that idea. You heat up the gas. It's not always pistons that do it, but it's always based on the idea that if you increase the temperature of a gas, it tries to expand, that applies a force to its surroundings. If you do the reverse of this, if you force the piston down, what happens to the gas?
Gas wants to heat up.
Yep, the gas heats up. So let's say the gas temperature increases. I'm going to try to not use the word heat too much in the way that we're used to using it, because heat is going to mean a very specific thing in this class. So, but yeah, it does heat up. The temperature increases. So this first one is how the power cycle works. Okay, if you heat up the gas with fire or whatever, you can use that rising piston to produce mechanical energy. You can lift things up, or you can cause motion, kinetic energy, or whatever. You can take that thermal energy that you've added to the gas and extract it as work. Okay. The second one, if you force a piston down, the gas temperature increases. That is the basis of the heat pump cycle and the refrigeration cycle. Okay. So a refrigerator, freezer, whatever, air conditioner, there's a compressor inside that forces a gas to compress. It increases the temperature of the gas, and then we'll talk about the specifics of it, but that's the main way that air conditioning or refrigerating works. For the power cycle, that's often associated with steam engines, and I think like people you tend to think sort of intuitively of steam engines as kind of stuff that happened in the 1800s. But even in modern nuclear plants, hydroelectric plants, this power cycle works the same way. It just isn't coal, for the most part, that's being heated up to increase the temperature of this gas. It's nuclear fission or, modern technologies, but the idea is still the same. Okay, so what kind of places does thermo arise? It does come up in electrical engineering, but not as much as in mechanical, aerospace, civil, and chemical engineering. And in those disciplines, it's just in all the places where you're doing calculations that involve both changes in temperature and changes in mechanical energy. This introduction, I always feel like when I first start talking about it, it's like a list of lists, but I don't really know how to avoid talking about it that way, so I'm still going to just sort of keep doing it. But you can break this class down, I guess, in a few different ways. The first is into power cycle, refrigeration cycle, heat pump cycle. You can also think about the types of calculations that we're going to use to analyze these things. So the types of calculations that we'll use. We're going to use conservation of mass. Conservation of energy. And conservation of energy is what's called the first law of thermodynamics. And then the third one we're going to use is the requirement that in a closed system, entropy can never decrease.
Is that the second law?
That's the second law, yep.
Okay.
Okay, and the part about a closed system is important because, like, for example, in a refrigerator, if you're only looking at the cold part of the like inside the refrigerator, the entropy is decreasing.
Yeah,
but
the entropy of the universe increases instead.
Yeah, but in order to cool down the carrots on the inside of the refrigerator, the back of the refrigerator is emitting heat to the environment, and that is producing entropy at a faster rate than you're losing entropy inside. So in the closed system, the entire room or whatever, there's a net increase of entropy. I don't think you guys have talked about entropy, done entropy calculations yet. Is that right? Have any of you had a physics class where you talked about it? That's right. Yeah, I think that's right. Maybe in physics 2, some teachers might talk about it briefly, but not very much. So we'll define entropy and we'll spend a lot of time on that in the second half of this class. And so really those are the only 3 types of calculations we're going to have. As far as, so in calculations that go from one instant to another instant. There are also, we'll see there'll be types of calculations that relate things in a single instant, you know, like the ideal gas law is something like that, an equation of state that says like, oh, well, if we know at this instant if there's a pressure and a temperature of this and this, then the volume has to be this. But these are the calculations that we're going to do that are going to relate what happens at 10:14 a.m. to what happens at 10:15 a.m. And we're going to do these calculations for the most part in 2 ways. We're going to analyze closed systems. And that's where the material that you're analyzing over this period of time is the same amount of material. So like right now, say those doors are more or less airtight, you know, say there's no significant amount of transfer of the air inside with the air outside, okay? Then if we wanted to analyze the thermodynamics of what's going on inside this room over a 5-minute period or something, we could treat this as a closed system. We know we could count all the air molecules and we know those are the same ones we're going to be analyzing in 5 minutes. Okay?
Yeah, so no change in chemical potential. I think it's what they call it. For closed system.
Yeah, not really chemical. It's really just like whether the atoms that we're looking at this instant are the atoms we're looking at the next instant.
I thought that was the term for it, was chemical potential.
Well, you could have, like, if you lit a fire right now, we'd still have the same atoms in here, but there would have been a change in chemical potential. You know what I mean?
From the physics standpoint, I think they use mu or whatever, and they call it chemical potential anytime you even have a change in particles or number of particles.
Uh-huh.
If I remember correctly. I've taken a thermal physics class many years ago, so I was trying to.
Yeah, right. So a closed system is over the time interval. We're looking at the same collection of particles. The second approach is called a control volume approach. So control volumes. And control volumes are for cases where it's not practical or possible to track the particles over the course of the time interval that you're looking at. So like if you're thinking of a water pump or something, you're analyzing what's happening inside of a water pump. You start with water that's in the pump, you know, and a minute later that water is out in the river or something, and it's a whole new set of particles that's inside. You don't want to have to try to figure out what's happening to that water in the river. What you'd rather do is just track what's happening inside of that volume, inside the volume of the pump, knowing that new material is always coming in and old material is always going out. So in this case, over that time interval, we're looking at the same volume in space. As material passes through. So if you think about different ways of executing a power cycle, one is a piston. In a piston, we'll be analyzing the gas inside the cylinder using a closed. It'll be treated as a closed system because that gas is locked inside between the piston and the cylinder, and it's just changing volume, changing temperature, okay? On the other hand, in a case where your power cycle is taking steam and running it through a turbine, at every instant, that gas is going from one side of the turbine through to the other side of the turbine. We won't be able to track that steam as it goes through, and so we'd be using a control volume approach in that case, okay? And so I think as we go through these calculations that happen from one instant to another, remind yourself, like, you're always going to be using one of these three things: conservation of mass, first law or second law of thermodynamics, and you're always going to be doing this analysis using either a closed system or a control volume. Be sure that you're clear to yourself on what that is. Who here loves vectors so much? All right. Well, there's not much vectors in thermodynamics, but there's something equally important. So we won't see vectors much.
Yeah, it's primarily just equations of state.
So it's what is going to replace vectors is a sign convention, and this sign convention is very important. So you will have a very important sign convention. And that has to do with what you call positive work and what you call positive heat. So let me just define these really quickly. So the heat we'll always call capital Q, and that is a change in energy of your system due to a change in temperature. Or let me reword that actually. Rather than a change in temperature, let's say it due to a temperature difference. Like between your system and the surroundings. The work, and this is the one that you dealt with in Physics 1. Work is a change in energy of your system due to the application of a force. Okay, so remember in physics 1, if you push on an object and it moves, you did work on that object. That's because you're applying a force to it. Heat probably didn't come up very much in physics, but if you lean an object against a hot surface or put a fire under it or whatever, the temperature of the object increases. That's an increase in energy, and that's due to heat. Okay. And so the first law of thermodynamics it's just conservation of energy. So you would think it would say something like the change in energy of your system is equal to the heat, and don't write this plus yet, plus the work, right? There's two ways to change the energy of your system. If you increase both of them, it increases the energy, right? But instead of that being a plus, it's a minus because of the sign convention that we're going to use for Q and W. Okay, so I want you to notice that this seems odd. WTF? Okay. So why is that? It is because the sign convention for heat and work, Q and W, follows what happens in a power cycle. Okay, so let me draw a piston again, a cylinder with a piston. Okay. Our system that we're following is the gas, so I'm going to just write system in here. Okay. And in order to raise this piston, you heat up the gas. That's supposed to be a fire. Okay. And so in a power cycle, energy comes in to the system through heat. Okay, and energy leaves the system through work. Okay, so, and that sign convention is going to stay with us through this whole class. Positive heat is heat being added to your system. Positive W is work being done by the system. In other words, energy leaving your system through work. Okay? So start wrapping your head around that now. you're gonna have to remind yourself of that in every calculation you do. Okay, is energy coming into the system or leaving the system through heat? If it's coming into the system, Q is positive. If it's going out of the system through heat, like you have a high temperature in your system, the gas that you're looking at is a high temperature, the surroundings have a low temperature, and energy is leaving the system through heat, that means Q is negative, okay? On the other hand, if your system is doing work, W is positive. If energy is being added to your system through work, you're pushing that piston down, W is negative, okay? And if you get those sign conventions wrong, it's going to mess up calculations. And you're not just going to get wrong signs and answers, you're going to get wrong answers, you know, because you'll be adding or subtracting something you should have done the opposite of at some step along a calculation, okay? So there's no real vectors to worry about, but you always have to keep this sign convention in mind. Any questions? Okay, let's stop there. And next time we will talk about properties, states, and processes. And this topic is sort of a formal discussion of what I was saying before, you know, like I made a distinction between what's happening at this instant versus what's happening from this minute to this minute. These three terms relate to those distinctions. Okay, so we'll talk about that. All right, well, I'll get this video and these notes posted on D2L. I'll check the problems. I don't think there's probably any problems we can do yet, so I think probably we'll just wait until Thursday, and then I'll be able to give you some kind of assignment after class on Thursday. And yeah, email me if you want to talk about anything, and I'll see you Thursday.
Yeah, same place, same time.
Yeah, that's right.